Hey everyone, welcome to this video. Let's talk about generative modeling. So previously in this course, we've talked about discriminative modeling, a lot of syllables. And an example of this could be you pass in a text of, congratulations, you just won a gift card, click here to redeem. And if our model has good weights, which can be thought of as like the knowledge or brain cells of the model, if our model has good weights, it will correctly determine that this text is spam rather than not spam. Or if we pass in a picture of a face, such as my face, if our model has good weights, it will correctly guess that it is a face and not a picture of, say, hands or feet, etc. So what happens in generative modeling? We pass in a string or text of generate new images of Kevin. If our model has good weights, it will generate really cool pictures or new pictures that have never been seen before of Kevin. An example you can see for yourself on the internet is something called thispersondoesnotexist.com. And as the name implies, none of these people actually exist. They have all been generated. Pretty cool. And if you check the bottom right hand corner, it will say style GAN 2. And later on in the course, we will learn about GANs. So yeah, a cool example of generative modeling in action. The first generative model we will learn is a variational autoencoder, also called a VAE. So to get started, first off, what is an autoencoder? An autoencoder compresses input data, uses the compressed input data from step 1 to reproduce the input data. So imagine our input data is this text of Kevin, where each of the letters appears twice. So 2 Ks, 2 Es, and 2 Vs, etc. And then maybe to save space in our computer, we will compress it to just Kevin, so it's one letter each. And then if we want to uncompress it or get the original data back, we can just take the compression and double the letters again. So hopefully this is a intuitive example of what autoencoder does for compression and then reproducing the input data. Autoencoders learn the most important information in data and do not use the less important information in data. And an autoencoder has an encoder, a lane space slash bottleneck, or in more simple terms, compressed data, and a decoder. So here's a diagram, right? The input data could be my original text of Kevin with 2 letters each. Then when we compress it to save space in our hard drive or disk, it's just Kevin with 1 letter each. And then if we want to reproduce the data, the decoder will hopefully do a good job and reconstruct Kevin with 2 letters each. But rather than work with text, let's say our input data is an image of me. It gets compressed, and if we have a good autoencoder, when it reproduces the data from the compression, hopefully the images are the same or close to being the same. Okay, so let's talk about the encoder first. Right here, it compresses input data. Later layers generally get smaller, and there are some customizable hyperparameters, such as the number of layers, the size of layers, the activation function. Now for the bottleneck, which is like the compressed data, contains the compression. If this compression is too small, the autoencoder will not learn enough important information about the input data and will have issues with reproducing the input data. What's the opposite problem if the compression is too big? Well, the autoencoder could just copy the input data and will not learn enough important information about the input data. And lastly, for the decoder, right here, uses the compressed input data to reproduce the input data, and later layers generally get bigger. And in autoencoder training, we will have a reconstruction loss, such as mean squared error, which we learned about earlier on in the course. And this reconstruction loss will measure how much different the input data and decoder output are. So when we compress this image of me, right, and then we try to uncompress it to reproduce the data, the reconstruction or the reproduction is not the same. My eyes are closed, whereas my eyes are open. So in real life, we would say this compression is really bad because it's not accurate when we uncompress it, and the reconstruction loss will be really high. In case some of you are wondering, why should I care about the reconstruction loss? Here's a quick review of what we talked about earlier on in the course. Imagine that we have a model that tries to determine if this is a picture of a dog or a picture of a cat. We pass those images to the model. Hopefully the model has good weights, so it makes good predictions. So it says, okay, I think this is a picture of a dog, and I think this is a picture of a cat. We use the error/loss to tell the model how correct its predictions are. So maybe the error/loss will tell the model, whoa, wait a second. That's a picture of a cat, not of a dog. You were wrong. We use that error/loss to update the weights, and hopefully the model has better weights, better knowledge, better brain cells, so that its predictions are better, so that we have a lower error/loss, and the cycle keeps going until, again, hopefully, our model has really, really good weights, so it is really good at determining if this is a picture of a dog or a picture of a cat. And this reconstruction loss, such as mean squared error, is for this part of the diagram. Now, there are some pretty cool things you can do with autoencoders, such as denoising autoencoders. You can also use autoencoders to eliminate noise or corruption from data. So here's corruption in this picture of me, right? My image is a bit more fuzzy, so to speak. In training, add noise to the input data, then compare the decoder output to the clean input data. So these are almost the same or are the same. So our denoising autoencoder has done a really good job of removing the noise or corruption. Denoising autoencoders learn the most important information in data and do not use the noise in data. So some other cool use cases for a denoising autoencoder, maybe the image is damaged and it's really good at repairing things, or maybe there's like sun glare or light glare in the picture, and the denoising autoencoder can remove the light glare or sun glare and make me look awesome again. Now let's start changing our diagram a bit. For the encoder part, we'll just use a square with the word encoder in it, and for decoder, we'll do the same. And for the compressed data, we'll represent that with a lane vector, which is like a vector or an array of numbers. And the decoder uses this array of numbers to hopefully reconstruct the input image that was compressed. Now, in case this seems like magic to some of you, like, wait a second, how can the decoder turn this array of numbers into an image? That does seem like magic to me. One way you can think of it is this. Maybe each value is like a feature. So 0.9 could be for the jacket value. And since the jacket value is really high, hopefully the decoder creates or reconstructs an image where I have a jacket on. And then maybe the eyes, the 0.99 could be the eyes value. So when the decoder reconstructs that image of me, my eyes are open and not closed. So yes, the lane vector will be the compression and will be a list of numbers. The lane vector is used to reproduce the input data. And a bad lane vector of like bad numbers or invalid numbers will give you an invalid image. And if you pass in different lane vector values, the decoder should reconstruct different images, right? So a high jacket value, I'm wearing a jacket. A low jacket value, I'm not wearing a jacket, I'm wearing a shirt. Now, let's get to the meat of this video, variational autoencoders. Instead of reproducing input data, we want to create new data, so we have to make some changes. Instead of the encoder outputting a lane vector for the input, the encoder will instead output potential valid values, called a distribution. It will have a mean vector, which is the mean of the distribution, a standard deviation vector, which will say how spread out the distribution is, and we will create a random, emphasis on random, latent vector called a sampled latent vector from the distribution. The sampled latent vector creates new data, and this new data will be similar to the training data. So this is a wall of text. What does this look like when we visualize it in a diagram? Here is our VAE or variational autoencoder in action. We have an encoder that gives out a distribution we'll have a mean vector and a standard deviation vector to like represent that distribution. From there, we get our sampled latent vector that the decoder uses to generate new images that have never been seen before. And as we mentioned, maybe sometimes this sampled latent vector has a high jacket value, so I'm wearing a jacket. Or maybe the sampled latent vector will have a low jacket value, so I'm wearing a shirt instead. All right, so those are the core ideas behind a VAE or variational autoencoder. I hope you enjoyed this video. See you all in the next one.